Okay, so I mentioned it briefly at the end of the last section, but I just want to spend a bit more time going over this point, as it's probably going to be one of the most important points as we move forward. So, what is a homomorphism? Well, this is just fancy terminology for a structure-preserving map. Okay, so what do we mean by structure-preserving? Well, first of all, let's just remember what we mean by a map. So a map, which I'm going to call lambda, is an assignment that takes an element from one set, we're going to begin with the set V, and just maps it into elements in some other set. So now the structure preserving part, if the set that we begin with has a certain type of algebraic structure, it could be anything, it could be a group or whatever, I'm going to take it to be a vector space. Structure preserving means that when we map into this target set, the target set has the same type of algebraic structure as the domain set that we used. So W is going to be a vector space. So this is fine. We know how to construct maps. We simply take an element from the domain space, and then we decide, or we assign an element in the codomain space to that particular element under the action of the map. So we would say that V maps to W, which is in the W space, where this W is, and now I'm going to use our bracket notation for the map, W is the action of the map acting on the element V. Okay, so now if we just consider visualizing this, we have our first vector space, then the target vector space, and we're constructing a map between these two spaces, which we're calling lambda. Now I'm going to give this lambda a particular name because it's one specific map from one element to another element. So what we consider when we talk about all of the lambdas together, we're considering the set of all possible lambdas that we could write down, and so forth. So I'm going to use a notation for this called homVW, which kind of stands for the set of all the possible maps which you could create between these two vector spaces. But these aren't just any maps that we can create, they're the structure preserving maps. So this homVW is the set of all possible structure preserving maps between these two vector spaces. So elements of this homVW space are going to look like this. They're just maps waiting for an input. So these are what the elements of homVW look like. And now the absolutely crucial point about this set of maps is that because they are structure preserving, which we saw in the vector space case means that they're linear maps, because these maps are linear maps, we can turn this set of all of them, this homVW, we can realize or give this set a vector space structure. So the set of all linear maps between two vector spaces, homVW, is itself a vector space. So I'm not going to show this too rigorously. I'm just hopefully going to be able to convince you with a few examples. So if we consider a single element in our domain space, which I'm going to call V, and now we consider possible linear maps that we could create into W. So I've written them, two of them here, lambda 1 and lambda 2. Now just consider for a moment what it would mean to construct the sum of these two maps and then act on this vector that we're starting with over here. So because these lambdas are linear maps, we're allowed to split the map up in the following way. We simply act with the map, each map individually on the vector, and then because we know that this lambda 1 acting on V gives us some element in W, which I'm going to call W1, we can then add the result of mapping lambda 2. And because these are simply just two vectors that live in W, we can vectorially add them using the W plus. So it might not be immediately obvious why this means that this lambda object is a vector, but if I just remove the input for a second, and we just think about these maps as objects by themselves, then we see that this is a vector, or it's being added as a vector using this vector addition which we've defined for W. And then just as equally we could consider something like if lowercase lambda is a scalar and we have another map which acts on something, this can easily be seen to just be the scalar multiplied by the result of the map. So these two properties that we're guaranteed to have these maps satisfy by the fact that they are linear maps means that we can consider the set of all of them to be a vector space, because we can show that it has an appropriate vector addition and scalar multiplication operation. I won't go all the way through and show that all of the axioms are satisfied, but you can take my word for it that they are. So the set of all of these map objects, kind of treated abstractly as objects by themselves, the set of all of them, Hom VW, is a vector space. And so by virtue of the fact that we've made this Hom VW into a vector space, we are guaranteed that it's going to preserve the algebraic structure. We can also work the definition the other way around. We can say that given that it's mapping between two vector spaces and preserving their structure, the map itself must have a vector structure. So all you need to remember going forward is that the set of all maps between two vector spaces is itself a vector space.